Okay, let's dive into this. Welcome back, everyone. Today, we are looking at a material that literally breaks all the rules of what we think a metal should be. We're unpacking a recent study straight out of the journal Materials Horizons that finally, and I mean finally, solves a decades-old scientific mystery. We're talking about the bizarre, completely rule-breaking nature of gallium. Take a look at the metal we're dealing with today. This is gallium. And yeah, what you're seeing is a solid piece of metal just melting into a shimmering puddle right in the palm of a hand. It's just pure visual weirdness, isn't it? Literally, just the natural warmth of human body heat is enough to trigger this phase change. I mean, it looks like a magic trick, or maybe some CGI out of a sci-fi film, but it is entirely real.
But, seeing this begs the ultimate question. Why exactly does this metal just melt in your hand? For a really long time, scientists obviously knew that it happened, but the exact microscopic mechanics of how and why it behaves this way, well, that remained strangely elusive. So today, we're going to shrink down to the atomic level to solve this mystery. And let me tell you, what we find completely upends standard chemistry.
Part 1. The Gallium Mystery, a counterintuitive density.
So let's start with our first major clue here, which is how it freezes. Usually, right, when things freeze into a solid, their atoms pack really tightly together, which makes them much denser. But not gallium. It actually has a lower density in its solid state than it does as a liquid, which means if you drop a chunk of solid gallium into liquid gallium, it floats. It's exactly like ice floating in a glass of water. And for a metal, that is incredibly rare. It's really our first big red flag that gallium atoms are organizing themselves in a highly unusual way.
Part 2. The atomic anomaly. A metal posing as a nonmetal.
Now, what's really interesting about this is that to figure out why it floats, and honestly why it melts so easily, we have to look at this massive atomic contradiction. Typical metals are usually held together by this sea of free-floating electrons. That's exactly why materials like copper are such great electrical conductors. But gallium? In its solid state, its atoms actually pair up and share electrons directly. These are called covalent bonds. And here's the crazy part. This is behavior we usually expect from nonmetals like carbon. So it's literally a metal suffering from a massive identity crisis.
For years, scientists just kind of assumed that these non-metal-like covalent bonds stuck around when gallium melted. But new data shows something wild. Let's walk through the steps here. Step 1. In solid form, those rigid covalent bonds are present, as we just talked about. Step 2. Right at the melting point, like when it's just sitting there in your hand melting, those bonds completely vanish. Boom, gone. And because the bonds break, electricity actually flows easier, meaning its electrical resistivity drops. But then, step 3. As you keep heating that liquid gallium up, the bonds mysteriously reappear. And this causes the electrical resistivity to just shoot right back up in this bizarre, totally nonlinear way. The bonds are basically playing hide-and-seek based on temperature. It's fascinating.
Part 3. The hidden surface order, the geometry of chaos.
And you know what? The weirdness doesn't even stop with electricity. Usually we model liquids as these highly disordered, chaotic entropic states, right? Just a jumble of atoms. Yet, scientists just discovered that the very surface of liquid gallium actually maintains a highly structured, rigid geometric pattern. But here is the real kicker. This ordered structure is unimaginably thin. We are talking exactly 0.85 nanometers. That is just about 3 atomic layers deep. So below that, you've got your typical liquid disorder, total chaos. But right on the surface, it's this perfectly organized microscopic grid.
And this incredibly fragile 0.85 nanometer architecture can actually be manipulated, which is huge for material science. Let's compare what happens when we introduce some outside elements to the mix. If the surface is exposed to oxygen, so causing oxidation, that geometric order is actually reinforced. It gets stronger. But if you introduce an impurity, say the element bismuth, it completely shatters that fragile surface order. It's just this unbelievably delicate atomic balancing act.
Part 4. AI solves the enigma, the tools of the modern detective.
So how did we finally see these tiny disappearing bonds and incredibly thin surface structures? Well, it takes some serious computational firepower, and this brilliantly illustrates the sheer power of modern science. To crack the gallium code, researchers didn't just go into a lab and run new physical tests. No, they built massive, large-scale computer simulations. Then they took historical experimental data that previously seemed completely contradictory, by the way, and fed it all into advanced machine learning AI. The AI was actually able to spot the microscopic patterns that human researchers had missed for decades, perfectly reconciling all those conflicting scientific papers. Pretty amazing, right? Part 5. The Technologies of Tomorrow, Beyond Semiconductors.
Now, you might be wondering, why go through all this trouble just to understand a metal at the nanometer scale? Well, because understanding a material's quirks lets us literally engineer the future. So, the crucial point is that right now, gallium is already critical for the semiconductors inside your smart devices and the solar panels on our roofs. But by finally understanding how its electrical resistance changes with heat and how that surface structure works, we can design entirely new alloys with completely adjustable properties. We're looking at a future of truly flexible, bendable electronics, highly efficient next-generation batteries, and advanced chemical catalysts. Literally, by mastering the anomaly, we master the application.
It really makes you stop and look at the physical world a bit differently, doesn't it? We took a metal that melts in your hand, zoomed way in to see it playing hide and seek with its own atomic bonds, and then used artificial intelligence to unlock its secrets for the tech of tomorrow. Which brings us to our final thought for today. What other secrets are hidden in the materials all around us? Because if something as fundamental as a seemingly simple piece of metal still has tricks up its sleeve, just imagine what else is waiting to be discovered under the microscope. Keep questioning, keep learning, and I'll catch you on the next explainer.